What's up, guys? Welcome to this little R session. So for today's session, we're just going to look at simulating Poisson processes under both fixed count and fixed window mode. So if there's anything you might want to revisit, it will be the theory on simulation of Poisson processes, and then maybe also the section on the exponential distribution where we looked at the probability integral transform. Also in terms of R stuff, okay, we'll just be writing a function, so nothing too complicated, but maybe one thing you want to check out is the so-called missing function. So just type $missing and read the help documentation on that. But in any case, I'll show you how it works. And yeah, let's jump into it. Okay, cool. So let's check out the template file and see what I've given you. Okay, now as always, we have one overarching goal. And in this case, the goal is to write a function which simulates time-homogeneous Poisson processes in either of two observational modes. Okay, so that's obviously going to be fixed window and fixed count mode. And I've already set a seed because we're going to do some simulations so that we always get the same results. Okay, and then I break it down into three tasks. Okay, so task one is just simulate a realization of a Poisson process with rate parameter 0.4 and a fixed count mode with n equals 6. Okay, so for 6 observations. And then plot the process trajectory. Okay, and then I've already populated some parameters there. Task 2, simulate a realization of a Poisson process with rate parameter 0.4 under fixed window mode on 0 to b, so some time interval 0 to b. For b equals 15, plot the process trajectory. I've already fixed b for you there. Okay, and then finally, task 3, write a function sim underscore Poisson p with the given input and output variables, which if n is specified, it will simulate at rand parameter lambda fixed count mode. Otherwise, if b is specified, it will simulate fixed window mode. Okay, and then I give you a function outline there with a return list and then some input parameters in lambda and b. Okay, so we'll just use that function skeleton. Cool, so let's kick off with task 1. Nice and simple one, simulate realization of a Poisson process with rate parameter 0.4 under fixed count mode with n equals 6. Okay, now how do we simulate a Poisson process under fixed count mode? Well, we appeal to the fact that the interarrival times are exponentially distributed. And how do we simulate exponential random deviates? Well, we use the integral transform method. Okay, so how does that work? Well, in this case, we already have a parameter for that distribution for the interarrival times, just lambda, and we're going to simulate 6 of them. Okay, so we're going to have to start out with saying, okay, let's simulate n random uniform deviates. Okay, so how we do that in R, we go R unif, so for uniform distribution, so runif, give it the parameter n, okay, because that's how many we're going to simulate, and it's going to be on 0 to 1, so random uniform 0, 1 deviates. Okay, so simulate u of a vector u containing n random uniform deviates. Okay, then next, well, we're going to apply the integral transform method. Okay, and from our calculations earlier in the course, we know that that's just going to be set sum vector t equals to minus 1 divided by lambda times log, and we can say 1 minus u, or just u because they have the same distribution, doesn't matter. And then this vector, which takes these u's that we've simulated just now, turns them into exponential random deviates. Right, so we have our exponential random deviates in our vector t. Okay, cool. So how does this help us simulate a Poisson process? Well, how are the interarrival times and the arrival times related? Okay, well, the interarrival times, add them up, and that gives you an arrival time. Okay, and you do that for each arrival time. Okay, so you create a vector s. Okay, and then we're going to say, well, calculate the cumulative sum of all of the ti's. Okay, so let's show you in a sec what that does. Okay, so let's just run this bit of the code then. Okay, let's go n. So n is equal to 6, u. So we can see we have 6 random uniform deviates. So you can see those are all on 0 to 1. Okay, and then we turn them into exponential random deviates. So we get our t's, and these are our interarrival times. Remember, so this is simulating how much time elapses between observations or increments in our process. Okay, so first we have 2.7, whatever units of time we're using, then 0.23, then 2.21, etc. Okay, so what is S supposed to look like? Well, S is just going to be the cumulative sums. Okay, so if you take 2.73 and you add 0.23, well, then you get the next one. Okay, so which is 2.97. Then if you add 2.21, you add that to 2.9, then you get the 5.19, and so on and so forth. Okay, so that's how we calculate the arrival times. Okay, so S is now our vector of arrival times. Well, what else do we need? Well, we need the increments of the process, and then we know that, well, at time 1, the count incremented from 0 to 1. At time S1, so which is 2.73, the process incremented from 0 to 1. At the next one, it incremented from 1 to 2, 3, 4, 5, etc. Okay, cool. So NT, which is just the process state, is going to be 1 to however many arrival times we had. So let's just go 1 to length S. We could have just written N, I guess, but this is more general, so yeah. I guess it doesn't matter. Okay, cool. So NT will now be the increments of our process. S will contain the time points at which it increments. So now let's plot the process. Okay, so what will the plot of this process look like? Well, let's go plot NT, and then we'll plot that as a function of S, right? So S goes on the x-axis, NT goes on the y-axis, so we'll plot the state, time, and there we go. Okay, but now we need to be careful, right? We're not just going to connect the dots because, well, the process remains in a particular state until it increments. Okay, so the type of plot we're going to draw is going to be a step plot. So in S or in R, what you do is say plot NT is a function of S, and then, well, the type of plot we're looking for is of S. So you can specify that it has to be a step plot. Okay. What else is there that we would like to specify? Well, I guess nothing really. Okay, so let's just plot that and then see what happens. Okay, so let's rerun the code. Excellent, and that's what we see. Okay, so indeed we see that the process increments all the way up to 6. That is correct. Well, we can see all the sort of random arrival times. One thing that's a problem here is we see that our plot starts out at 1. Okay, and it starts out here at, what was that? I think it was 2.7 or whatever our first arrival was. Okay, so this plot is cool, but it's not quite correct yet. Why? Because remember we said that our process counts from 0. So we sort of started our plot off here at the first observation, but really if we want this plot to accurately reflect the trajectory of the process, we need to start out at 0. Okay, so one way we can do that is we can just prepend the time and the state vector with zeros. Okay, so we go concatenate 0 in t. Okay, so that's just going to take, let me show you what this looks like. So nt goes 1, 2, 3, 4, 5. So what does concatenate 0 in t look like? Well, that's just 0, 1, 2, 3, etc. So what does s look like? 2.73. So let's concatenate 0 and then s. Okay, so we just prepend everything with a 0. We redraw the plot and we see, okay, cool. So that's a more accurate reflection of the trajectory of the process. So yeah, just to be careful when you plot these things. That thing makes sense. Okay, so let's leave it at that. I'm just going to kill off that plot for a sec, and let's go to task 2. So task 2 says, simulate a realization of the Poisson process with rate parameter 0.4 under fixed window mode on 0b for b equals 15, plot the process trajectory. Okay, so same story as before. Okay, cool. So how do we simulate things or how do we simulate a Poisson process in fixed window mode? Okay, so we're going to again have to generate inter-arrival times, which are exponentially distributed. Yay, we're going to have to calculate their cumulative sums so that we get the arrival times. But what's different about fixed window mode? Well, for one, we don't know how many arrivals we have, right? Because we observe the process for a fixed window, that number is random. So if you think about generating random deviates now for that, or simulating the process on that, well, we need to somehow get the process to figure out what n do we have for our particular realization. And we said that the algorithm goes as follows. You keep generating arrival times until you exceed the window. Then you step one back, and that's your last arrival time. Okay, so you essentially start out with simulating too many observations. Okay, so strategy we're going to follow is not a particularly efficient one, but it works. Okay, so we're going to just pick some m. Okay, it's just some value for the number of observations that we're going to generate. Okay, and we're going to generate, how do we pick this value? Okay, let's go round, and we're going to generate 3 times the number that we expect to see in this interval under the particular model specification. So 3 times b, which is the width of the interval, times the rate. Okay, and the rate parameter is just lambda. Okay, there you go, and we'll just round it off. Okay, so that we have a whole number. Okay, there you go. So what does m look like? So m says, okay, generate 18 observations. Okay, cool. Right, so let's go then. Okay, well, how about those inter-arrival times? Let's simulate them. Okay, that's just going to be easy enough. We can just basically copy our code from before. The only thing we need to change now is that we're going to simulate m random uniform deviates. We're going to change m of them into exponentials, and then we're going to turn them into arrival times s. And okay, well, that will be our set of arrival times. Okay, so let's simulate all of that. And let's look at the arrival times that we've generated. Okay, so we simulate the arrival times, and we see that the arrival times this time around goes 0.5, 0.86, 2.8, blah, 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 blah. And then at some stage, we see that, okay, actually, it exceeds the window over which we're trying to simulate, right? So the window which we're trying to simulate is b equals 15. So we've already got one arrival time there over that limit, and then it'll go on all the way up to 39. Okay, so that's not cool. What we need to do now is we need to trim that vector, okay, and we're going to sort of reassign s to be s such that s is less than b. So take all the elements which are less than b, so the endpoint of that window, and keep them. Okay, so let's look at what s looks like now. So s is going to run all the way up to the 13.97. Okay, so we've chucked all of these additional simulations. Okay, and that sort of mimics the scheme that we had on paper. Okay, cool. Now what we need to do is we need to find, I guess, n star, right? So what is n star? N star is now the length of whatever that vector is, right? So remember, n star is some random quantity. It's how many arrivals you have. Well, check the length of that vector. That gives you n star. Okay, cool. All right, so we've then got our inter-arrival times. We know how many there are. And then, well, the state variable of the process just goes 1, 2, 3, etc. So 1 all the way up to n star. Cool. So that's the state trajectory. Right, let's plot the process now. Okay, well, we've got everything we need. We can just borrow from our previous plot. Okay, so again, we'll prepend everything to start from 0 so that we get a neat plot. And we'll plot the state variable as a function of the arrival times, plot a step plot, and yeah, okay, cool. So let's just rerun everything. Okay, cool. And what do we see? So we see our process start out at 0. We've got our sort of random inter-arrival times. It goes up to 8. So let's just see n star. How many? Oh, indeed, there were 8 observations in this window. But let's look at our plot, and then we see, okay, our plot ends off at 8, but it doesn't quite end off in the window that we've observed. So remember, we've observed the process from that last arrival all the way to the end of that window, right? So really, actually, what we want to do for this plot to make sense is we want to continue our plot to the endpoint. Okay, cool. So what we do now is, for this plot, fixed window mode, what we do is we append now the state variable vector. Again, we just repeat the last one. Okay, so n star. So it's going to sort of connect that last bit of the plot there to an endpoint at the same level over the entire window. Okay, so append with n star, and then we'll go 0s, and then again let's just repeat. Oh no, we're not repeating there. What we're doing is we're going to the endpoint of the window, so that'll be b. Okay, so let's replot the trajectory, and there we go. Okay, so to see what I'm on about, let's just go a b line, and we want to draw a vertical line, so v, and we want to draw it at b. Okay, and I'm just going to change the line type, so LTY to 2, and then I'll go color, and I'll make it lime green. Okay, so you can see the endpoint of the window. Okay, cool. Right, so that takes care of the plot under fixed window mode. Okay, and then now we also have schemes for simulating under fixed window mode and in fixed count mode. So let's go on to task 3. So task 3 says, write a function sim underscore Poisson P with given input and output variables, which if n is specified, it will simulate at rate parameter lambda, fixed count mode. Otherwise, if b is specified, it will simulate fixed window mode. Okay, again at rate parameter lambda. I've given you a function body there. Takes input n lambda b. Okay, so everything that we actually need that we saw in our previous simulations, and then we wanted to return a list of things, which are the arrival times, so s, the inter-arrival times t, and then the state variable nt. Okay, and then I've got a hint for you here. Use missing. So missing is a function in R. Okay, so what we're going to do is we're going to use this missing function to determine which parameters are specified if not, and not. Okay, so what I'm just going to do is I'm just going to go to the earlier code. I'm just going to comment some of it out. Okay, so let's check the plots there. Okay, so let's start. So we're going to have a bunch of if statements, right? So maybe the first thing we want to check is, well, what does missing do? Okay, so let's just go question mark. So missing. So does a formula argument have a value? So missing can be used to test whether a value has a specified argument to a function. So missing x, so a formal argument, and then what will it return? Or it will return true or false if something is missing or not. Okay, so maybe the first thing we want to check is if maybe someone by mistake specifies both n and b, right? Okay, so say the user goes and doesn't specify any parameters, then it won't know what to do, it'll spit out an error anyway. Okay, but say someone gives lambda, they give b, but they also give n. Well, then that's an error, right? So maybe we just want to check that quickly. Okay, so we're going to go if, and then we're going to check a bunch of things, but we'll get to the checking now. If it checks that, maybe we want to sort of print an error first. Okay, and so input error, oh gosh. And we're going to say the input error is both n and b fide. Okay, and then we're going to go colon, semicolon, and then we're just going to return null, right? Because we don't want to return or do anything at that stage. Okay, now what are the things that we're going to check? Well, the first thing we're going to check is we're going to check if n is not missing. So if n is not missing, it is specified. And then we want to check another thing, which is b missing or not missing, I guess. Okay, so we go is not missing n, so that means it's specified. And if not missing b, okay, then return that error code. Okay, so that's just one error check that we'll do, and that's fine. Okay, so if the function runs, it gets past this point and says, okay, there's no issue, well, then we need to decide, okay, well, which simulation scheme do we use? Well, we can just sort of reuse that, right? So if n is specified, so when it's not missing, we wanted to run the first iteration of the algorithm. Alternatively, if B is not missing, so B is specified, then it'll run fixed window mode. Okay, and then what it's going to do in each of these configurations, it's going to populate the arrival times, the inter-arrival times, and the state variable. Okay, so whichever one it runs, sorry, I have to change that to B because we're actually checking for B there. Idiot. So in each of these configurations, we're going to populate an S and a T and a state variable NT, and that's what we're going to return. Okay, so where do we get these bits? Well, we've already wrote those, right? So n is specified, so lambda will also be specified in our function. So let's just borrow everything we've got here. Okay, and let's plug it into the function here. Cool. So if n is specified, so when it's not missing, you run this configuration of the code. It goes u equals run if n generates, applies the integral transform method, generates inter-arrival times. From the inter-arrival times, generates the arrival times and the state variable, and there you go. Okay, so it will have populated these things, and then our function will return a list with the arrival times, with the inter-arrival times, and the state variable. Cool. If B is specified, so when it's not missing, then we'll go fixed window mode. So let's borrow everything from here. Okay, and then B will be a parameter in the function. Okay, so let's plug that in here. Cool, does that make sense? Yes, it seems like it makes sense. So let's hope this doesn't explode in my face. Okay, so specified our function. Okay, let's go res equals sim Poisson P, and then we're going to simulate fixed count mode first. So we're going to specify n equals 6, lambda equals 0.4. Okay, so this should simulate in fixed count mode, and let's see what it does. Okay, and indeed, what does it do? Well, we say we want 6 inter-arrival times, etc., and indeed it does so. Okay, perfect. It's awesome. Let's see what happens if we don't specify n and we specify b. Okay, so we specify b to be 15. We rerun the code, then that should generate something on 0 to 15, right? So we don't know how many. Let's see how many we see. Okay, and this time around we only see 4. Okay, so let's maybe run another simulation, different iterations, so we'll see. Okay, cool, indeed. A random number of observations are generated each time, and that's what we expect to see under fixed window mode. Okay. Well, what if n is also specified? Well, n equals, I don't know, 2. So both are specified now. Let's run that. And it says, oh no, input error, both n and b are specified, and indeed it returns null. Okay, cool. Now, yeah, we can probably even prove this function even further with more error checking and stuff, but I mean, this is close enough for rock and roll. And you should also be able to use this function to simulate trajectories for a process and maybe conduct simulations if you like. Okay, cool. So I guess that's that for this one. I'll leave a problem up for maybe I don't know. I'll leave a problem up for you guys to check out, and then I'll see you in the next one. Cheers.